Today we're going to be talking about arithmetic sequences. This is going to be Unit 1C, Arithmetic Sequences. It'll be in Chapter 5 of the textbook, Section 7. That is our topic for today with your notes page, Arithmetic Sequences. And again, this is where it's in the book. We're going to start today by figuring out what is an arithmetic sequence. And then once we do, we're going to write an n-1 rule and a simplified rule. So our objective today is to write n-1 in simplified explicit rules for arithmetic sequences. Again, if at any point in time you need to pause the video to kind of make sure your notes page is in order, please feel free to do that. So we're going to start with a sequence that involves two characters over here at right. They're Gumby and Pokey. They're actually part of an original claymation animation that was done over 50 years ago. And it was done by, these figures were originally made out of clay, think Play-Doh, and they would film it by taking a picture and then slightly moving them and taking a picture and slightly moving it. If you ever made a flip book when you were little where you took like a pad of Post-its or something and drew a picture and then flipped and saw the figure move, it was kind of along those ideas. The original Disney movies, like pre-Pixar days, like Snow White, Cinderella, they also used this idea, except instead of photographs, they actually had artists drawing those frames. So our sequence is the 24, 48, 72, 96. And in this particular case, it happens to be the number of frames. Think of it as the number of pictures. And the 1, 2, 3, 4, which would be the first term, the second term, the third term, those numbers in this particular case actually represent the number of seconds. So you're looking at 24 pictures per second to get smooth movement, to make it look not like it's jumping. So my question first off is, what if I wanted to know what a 7-second video would be? So I want you to imagine putting a 7 out here. How many frames would I need to get a 7-second video? So my question is, did you get 168? Now, there are two ways to look at it. The first way would be to look at this sequence and see that you're adding 24. And oh, yep, adding 24. And so out here, take 144 plus 24, and that would give you the 168. The other way is to notice there's a pattern, like we did with the last section with the charts, where there's a pattern between the term number and the output, where you're multiplying 1 times 24, 2 times 24, 3 times 24. And that, if you take the 7 times 24, will give you the 168 as well. That method is going to be a lot easier to come up with that explicit rule to get to the 100-second video. How many frames for a 100-second video? What would that be? So can do it in our head even without the calculator. 24 times 100, did you get 2,400 frames? So in order to make just a 100-second video, rather, you would have to have 2,400 frames. So my question to you is, let's get that explicit rule. Let's get, that n, that variable in there. So we're going to let n represent the number of seconds. Let's just come up with an expression first, and then we'll make it into an equation. What do you have to do to n to get the number of frames? Well, what we just did is we multiplied it by 24. Now you're going to notice that because it's a coefficient with multiplication, it has to be written in front of the variable. Now to make a rule, we need an input and an output. So we're going to need an output variable. And when we do arithmetic sequences, the book loves A of n. I don't know if the A was meant to be for arithmetic. It doesn't hold true in our next section. You'll see that when we talk about our next bit of material in the next video. But A of n is what the book uses. Now, I need to make sure you understand that if you use function notation, this variable right here in the parentheses is telling you what variable is the input variable. You would never have, for instance, A of x equals 24n. This variable has to match that one. Okay, so that would be our function rule. So if we were to put that, 100 in for n, 24 times 100 would give us an output of the 2,400. So the next one is to take a look at the toothpick triangles. So imagine you had a box of toothpicks and you were just kind of making triangles out of them. It would take obviously 3 toothpicks to make a triangle. Now, when you go to make the next triangle in the way that we've done here, it is not 6 toothpicks you would need, but 5 because they actually share a toothpick. And you'll notice if we were to add another triangle to give 3, it would be 7 toothpicks. And here is that, and then we add 2. So you're kind of noticing that every time we add a triangle, we are adding sort of those 2 toothpicks. Do you kind of see a pattern here? So you add toothpicks every time, but we sort of had this starting value of 3. So, can we come up with a rule that would give us the 13 triangles or 120 triangles? Can you come up with a rule right now? And I would recommend that you pause the video if it's not coming to you and think about it a little bit. How could I get a rule like we did in this slide before that was the A of n equals 24n? What kind of rule would work here? Okay, I'm hoping that you took a little bit of time to think about it. I gave it kind of a little clue here. So, how do I get the 3 for the first and 5 for the second and 7 for the 3? Now, you'll notice that we're going up by that 2 every time. And when we were talking about our tables, you're going to remember we said to put that in front. So right now we're thinking this might be the rule. But if I put 1 in there for the first triangle, notice I'm only getting 2. If I put 2 in for n for the second triangle, notice I'm only getting 4. And each time you're going to notice that you are 1 short, so it needs to be a +1. Now let's think about the triangles. A way to think about this is that 1 is the original toothpick that you started with, and then every triangle after had to add 2 additional toothpicks. So now how would we get for 13? 2 times 13. Do the multiplication first, add second, and you should see that you would need the 27 toothpicks. So these are both what are called arithmetic sequences. So we need to kind of tie these ideas into what does that mean? Well, what you're going to notice in each case is the sequence always adds the same number between terms, whether it's a 24 or whether it is a 2, you're always adding the same number. So the recursive rule, that's what these are, a recursive rule, always adds a constant number, or by the way, it could be subtracting. So you could be adding a negative and have the sequence go down, but it's either adding or subtracting the same number between terms. So that is going to be what an arithmetic sequence is. So in your vocab section, just write arithmetic sequence. Do not write the whole definition out, but just so you know that's what we're talking about today. It's a sequence in which the difference between any 2 consecutive 2 terms next to each other is the same. Now, we just talked about the fact that in the Gumby and Pokey, it was a +24, and in the toothpicks, it's a +2. Those 2 numbers, that is called the common difference. So when the difference between consecutive terms of a sequence is constant, the difference is called the common difference. So back here, this sequence would be an arithmetic sequence because you are always, in this case, adding the same number, and the +24 would be called the common difference. When writing a function rule for a sequence, the input is going to be the number of the term, and the output will be what that term number is. So your input would be like the n, the value would be the a of n. So this is the term number, and this is the actual number that's sitting inside the sequence. So just look at these really quickly, pause the video, and what I want you to do, in your work section is just 1, 2, 3, 4. Is it a yay or a nay? Yes, that it's arithmetic, or no. And if it's yes, write down what the common difference is. Pause the video and do these 4, please. Okay, so let's take a look. First one, yes or no? And the answer is no. You add 5, but then you add 10. Not good. Next one, it's going down, but is it going down by the same number? 4, take away 3, take away 3, take away 3. This is a yes. The common difference would be -3. Is this one an arithmetic sequence? Again, it's going down. I'm taking away a half, but now I'm taking away a fourth. This is not an arithmetic sequence. This one, -4 to -8 to -12 to -16 is a yes, and the common difference is -4. So do you understand arithmetic sequence, what it is, and do you understand what common difference is? So our next job is to figure out how to write an explicit rule for any arithmetic sequence. And that's where we're going to start now. So I'm just going to give you another sequence. Here it is, 5, 8, 11, 14, 17. And right now we're going to come up with what's called the n-1 function rule. And we'll talk about cleaning that up later. So the first term is 5, the second term is 8, the third term is 11, the fourth term is 14. The first thing you need, is it arithmetic? Well, let's see, from 5 to 8 and 8 to 11 and 11 to 14, what is the common difference? It is an arithmetic sequence because that number is always the same. Did you get? +3. So again, like the toothpicks where I started with something, then I added 2, and then I added 2, and then I added 2, I'm adding 3 each time. So what I want you to do is just, we're going to have a rule in a second, basically a formula, but I want you to understand where it came from. So the first term, a of 1, is 5. The second term, a of 2, you take that 5 and add 3. Are you with me? Which would give you the 8. The third term, you take the 8, the 5 plus 3, and you're adding another 3. 8 plus 3 will give you 11. Now, the fourth term, you still have the 5, the 3, and the 3, and you're adding another 3. And I'm holding this out so you can kind of see the pattern. Notice that every time there's the original, and we're adding a 3 or 2 3s or 3 3s, or if you go back to the first term, we didn't add any 3s. So you're always taking the first term and adding some number of 3s. If it's the first term, you don't add any 3s. The second term, you're going to add 1 3. The next third term, you're adding 2 3s, and so forth. Now, what I want you to notice, we want to write a general rule for any number of terms. We want a of n equals. Notice that we're going to have a 5 plus 3 in our rule times. Now, this is the thing that's varying. And I want you to look that when we had the fifth term, we needed to add 4 3s. And when we had the third term, we had to add 2 3s. So we're always starting with the first term, adding 3 times 1 less than whatever n was. So here's our rule. This is called the n-1 rule. You take the first term, add the common difference times n-1, and that is our function rule for this sequence. So let's test it out. Let's put in 5 for n. Will we get the 17? So down here, we're going to put 5 minus 1. We're going to do what's in the parentheses first, and you're going to get a 4. Now, please remember, you have 5 plus 3 times 4. You need to multiply before you add. 3 times 4 is 12. Add 5 is 17. And sure enough, it gives us the fifth term. So this is the n- rule for the sequence that will give us the value of any term. It's an explicit rule. So here is the formula, and you're going to want to write this in your notes page and, under formulas, right there. Okay. So let me describe which each one is. The a of n is going to be your output. It's going to be the value of the nth term. The a in this general formula is your first term. So in the last case, it was a 5. The D is going to stand for the common difference, and you were taking the first term plus the common difference times n-1, and don't forget that the n is the term number. So this is our general equation for any arithmetic sequence. So if I was going to look at this sequence, all I have to do is say, okay, well, a of n equals the first term, 5, plus what's the common difference? 3 times n minus 1, and there's my formula. Okay, so let's figure out what would the 100th term be? That's the value of an explicit rule. So you're going to put 100 in here right now. Can you find a of 100 using the n minus 1 rule? Please pause the video and come on back when you're set. So did you get, of course, that you're going to multiply by 99, and you're going to multiply first and then add the 5, and you should have got 302. And that's how we write an n minus 1 rule. So now I'm going to give you a chance to try that. Now, this formula should be on your notes page. I'm going to click off. Okay, so now here's your chance to practice. What I need you to do for these 3 problems, they're all arithmetic sequences. I'm telling you that. You're going to write the n minus 1 function rule, and then you're going to use it to find the 20th term. And I'm giving you a little hint here. Don't forget, you got to start by knowing what the common difference is. So what I'd like you to do is pause the video, do all 3, come back, and we'll walk through them together. Okay, let's see how you did. First thing is, what's the common difference here? Did you get that you're adding 6 in between terms? To write the a minus n, the n minus 1 rule, you're going to first write a of n equals, and then the first term would be the first thing you write. First term is 3 plus the common difference times n minus 1. Now that should be able to get you any term, but we want the 20th. We want a of 20. So you're going to put 20 in for n and do the math. Make sure you're using your order of operations correctly. Parentheses, then you're going to multiply, then you're going to add. And did you get that the last term, or rather the 20th term, was 117? Okay, the next one, common difference this time is going to be a negative. It's going down. Your first term is 12. So you're going to have a of n equals the first term, 12, minus 2 times n minus 1. You're going to substitute 20 in. 20 minus 1 is 19. You're going to use your order of operations. And did you get that the 20th term should be negative 26? The next one's a little bit harder to see here what's going on, but I want you to remember that 1 is 5 over 5. So remember, rewrite that so you can see that. So you're going to have a 2 going to a 5, going to an 8, going to 11 in the numerator of these fractions. Common difference would be to add 3/5. So the a of n would be the first term plus the common difference times n minus 1. I'm going to substitute 20 in. And now 19, remember this 19 is over the invisible 1. So 3 times 19 over 5 times 1. And then add the 2/5. And did you get that it will be 59/5? Now, I know that a lot of you right now are saying, ooh, I want to write that as a mixed number, but look at your sequence. It's writing them as improper, so you can leave that as improper. And you'll find that in algebra, we often do leave things as improper rather than mixed numbers. And I will talk about that as we go through. Okay, so here's a real world example, and then we're just going to talk about simplifying these a bit. So write the first 5 terms of a sequence. Sarah started the savings account with $500 and deposits $25 each month. So we want to write the sequence first. So she's starting with that, and she's adding $25 each month, right? Okay, so there we go. Can you write a function rule to model this sequence now using an n minus 1? I'm going to ask you to pause and go ahead and give it a try. Okay, let's see how you did. We're going to write a rule. Did you define your variables? I'm going to use a of m to be the account balance in dollars. I'm going to let m be the number of months. So you don't have to use n. I'm just using some different variables to get you comfortable with that. Did you put the dollar sign in your definition? Okay, so now we're going to write the rule. A of n equals the first term plus the common difference times the n minus 1 rule. In this case, it's m minus 1. And now I'm going to say how much would you have in 2 years. Now you got to be careful. Here's with having that months is important in there and didn't just put time. Years isn't going to be m, months is. So 2, you would not put a 2 in for months. You should have put in a 24. And again, 24 minus 1 would be 23. Multiply it by the 25 and then add the 500 and you would have $1,075 in there. Okay, so that just gives you an idea where some of this is used. Okay, so we're just going to take it one step further for today, and I'm going to give you 2 different methods. We've already done one of them with our tables in the last section, but I'm going to show you how to simplify these rules. The first one is, can you see that simplified rule right away? So I made this into a table, so like we had in the last section, just so you can see we did it this way before. So the first is 5, the second is 8, the third is 11, and so forth. When we were trying to come up with a pattern, we'd say, oh, add 4, that doesn't work. Multiply by 5, that doesn't work. But, oh, look, I'm seeing this 3, common 3 going down there. And we said, oh, well, you'll put that in front of the input variable. So f of x will equal 3x. And you'll say, hey, I think this is my rule. I'm going to try it. If I put 1 in, 3 times 1 is 3. Darn, I needed 5. Well, let me try 2. 3 times 2 is 6. I needed 8. And I'm always off by the same number, which in this case would be 2. So I am going to put a plus 2 out here. And that's how I can get my simplified rule. No longer is the input variable saying take away 1. And you can use x and f of x. You can use n and a of n. Just get comfortable using different variables. And if I check this rule, like we did in the last section, let me just put 3 in. So, right, I should get an 11. 3 times 3 is 9 plus 2 is 11, and I'm feeling good about that. So that's one method, is something that we already did. Now, the second method is using some algebra, and I've kind of covered this up because we haven't talked about this year yet. But can I simplify this using algebra properties? So the first thing I want you to notice is, almost we could cover up for a second. Let me just take the slide. And I want you to think back to last year. How could you simplify something that had a number times expression in parentheses? And you might remember something called the distributive property. So what if we were to do the distributive property here, and you would take 3 and multiply it by the n, minus 3 times the 1. Do you remember doing that last year? That's distributive property. So the first step in simplifying the n minus 1 rule would be to do the distributive property. Now the second is, is there anybody in here that are what are called, wait a minute, sorry. First of all, let me do the commutative property just so you can see this. But notice that the 5 here and the minus 3 can come together, but they're kind of separated by the 3 ends. So what if I do the commutative property? I switch the order of these two, and then you can see those guys right next to each other. These are like terms. Now, you don't have to write this step, but I'm doing it so you can see. I switched the order, commuted, 5 take away 3, and there is the simplified rule once I combine like terms. So either way, whether I use the method that we kind of talked about in the last section, kind of an intuitive approach to get to that multiplying the input times 3 and adding 2, or if I do the algebra, either way, I'm going to get the simplified rule. And again, it doesn't matter if it's an n and an a of n or an x and an f of x, but what you do not want to do is have f of x equals 3n plus 2. Those variables have to match. So the simplified form is used extensively, not only this year, but throughout math as well. So what I'm going to ask you to do right now is, can you try to use both methods? The first one, kind of the intuitive, like, okay, what goes in front of the x and sort of adjusting it. And then the second one is going to be using the n minus 1 rule. So you first have to come up with the n minus 1 rule and then simplify it. And we're always going to check to make sure our rule works. So it is imperative right now that you pause the video and try both of these. Okay, so let's see how you did. What was the common difference? Did you get a -4, which means that's going to go in front of the x. And now I'm trying to figure out, what do I have to do to adjust it? So if I was to put 1 in for x, I would have -4, but I need 11. What number do I combine with -4 to get 11? That's sort of the question. And did you get that it would be 15? 15 and plus a -4 would give you a positive 11. So I'm thinking that this is my rule. I'm going to check it with the fourth. Now, if I put 4 in, I better get a -1. -4 times 4 is -16, and add 15, sure enough, is -1. So this looks like a good function rule for this sequence. Okay, the next one, we're going to do the n-1 rule and change it. So the first thing is, all these are confusing me. I'm going to make all of these look the same as we talked about when we were doing our patterns a long time ago. And I'm going to make them all improper with the same denominator. So 12 divided by 4 is 3. 4 times 4 is 16, plus 1 is 17 fourths. I would have 10, 11 halves multiplied by 2 would give me 22 fourths. And now I can see the pattern. And do you notice that I'm adding 5 fourths each time? So when I'm adding 5 fourths each time, here comes my n-1 rule. First term plus the common difference times n-1. In order to make this work, I'm going to do the distributive property. 5 fourths times n minus 5 fourths times 1. And these two around the n are like terms, so I'm going to commute and put them next to each other, and I'm going to make that 3 have force because, in order to do that, they have to have the same denominator. So 12 fourths and the -5 fourths would give me 7 fourths, and there is my explicit rule. Does it work? I'm a little more nervous with this one, so I'm going to check it by putting a 3 in. So when I put the 3 in, I do f of 3. Now, remember that he's over the invisible 1. I'm going to get 15 fourths plus 7 fourths, which truly are 22 fourths, which is that term. So method 1 is sort of an intuitive approach. Method 2 is an algebraic approach. So if at this point in time, if you want a little bit more practice, this would be it, or I should say this is your extra practice. So you are going to right now pause the video and try these 3 problems. Okay, let's see how we did. Common difference on the first one was +2. It's an arithmetic sequence, common difference of +2. So I am going to put the first term plus the common difference times n-1. There is my n-1 rule. Distributive property and combine like terms, or do the intuitive approach, and you should have gotten 2x plus 1. If I was to put 5 in, 2 times 5 is 10, plus 1 is 11. Is the next one arithmetic? It is. Its common difference is to take away 5. I'm going to write the first term, which is 17, minus 5 times n-1. There's the n-1 rule. Now, if I do distributive property, I'll get minus 5n. Now, be careful. A negative times a negative will give me plus 5. So you should have negative 5x plus 22. And again, if you have this as a of n and an n over here, that's fine. I'm just trying to get you used to using different variables. And down here, if you notice, this one is not arithmetic, because here you are adding 5, and then here you are adding 6, and here you are adding 7. You're not adding the same term, so we cannot write a rule for those. And there is another practice of writing the n-1 and the simplified rule. So finally, just to show you that you could do this off of a table, here is the first term is 0.165 and so forth. We're going to use an equation to model each of these. So if I wanted to do my n-1 rule or my explicit, I'm going to start by defining variables. And I'm going to let d be the number of days, and I'm going to let g of d be the growth in inches. Don't forget your units. And I'm going to write a rule now that's going to use these two variables. So in order to find the common difference, take this minus this, right? The bigger one minus the smaller one. That's what you're adding. And don't forget that's your first term. Just so happens in this case that when you take 0.330 minus the 0.165, it is 0.165. So it's the first term plus the common difference times, in this case, the d minus 1. And if you do your distributive property and combine up like terms, this would be your explicit simplified rule. So the n minus 1, d minus 1 rule, and here's the simplified. How about if you pause the video and try this one? We'll come back, and this is the last example for today. All right, you might have different variables for me. I use d for the number of days and h of d for the height in inches. I put h of d equals the first term, and you'll notice it's the same common difference here. The plant is growing at 0.165 inches per day times d minus 1, and that is your, quote, n minus 1 rule. Now, if you distributive property and combine like terms, which is what I'm showing you the distributive property here. And now this, take away the 0.165, there is your simplified rule. So again, if you need to go back, take a look at any of the examples, feel free. And the filled in notes page will come onto Classroom for you to see at some point. So that will be accessible. So guys, we learned about what an arithmetic sequence is, and we learned how to write an explicit rule, two different ones, the n minus 1 and the simplified rule. Now we're going to have a little chance to practice with it. So give it a practice, and I will see you soon.